divided by OVR times the KVA of the load. Now, your answer is going to be rated in KVA. Remember that. So if you get 0.902, that's 902 watts because it's 0.9 KVA. Okay, remember that. Now remember how this goes. We do this first, right? And we get our equals and then we put in a bracket. I don't like this little thing that we do here, but we do it anyway. They show it. Okay, and that's how we do it. The buck is exact opposite of this. Exactly opposite. So the buck is going to be ICV minus OVR divided by ICV times the KVA of the load. Okay, once again, put in our brackets. That's how I want you to solve all on your exam buck boost transformer sizes. That formula. Output voltage required. Hold on real quick. Okay, per the nameplate, for what the question asks. Question wants 230 volts. Input circuit voltage, what do we physically have? Those are the values I want you to put in. Because remember, this formula is a little bit off when we actually do the volts per turn, right? When we do the volts per turn, that's actually solid, real field numbers. But for exam, I want you to do that. Yes.
I was just asking, so if the answer is gonna be in KVA, you keep that in KVA?
Yes. Yeah, because it's going to get, so when you get 0.532, right? That's really a little over a half a KVA. So you might see 0.5 KVA, 0.75 KVA. Yeah, you can change it to watts if you want, but then your answer's in watts. Does that make sense?
Yeah, it just makes an extra stuff.
It does. So this way it just gives you, most people freak out, they're like, I don't get 0.78. Well, that's 0.78 KVA. So it's 780 watts. So that's why we keep it in the KVA, because transformers are rated in KVA, they're not rated in watts.
Yeah.
Which sounds dumb, right? Money, $10,000 is still 10K. 10K is still $10,000. We don't rate transformers in dollars, we rate them in Ks. Does that make sense? That's how we do it. So 0.5K, $500. How you do it. These are the basic rules. Now, some of you are good on transformers, some of you, we can go over them again, we're gonna kind of go down the list. Some of you didn't make last week. Gotta ask you. Do you think that's something that the school should do every year?
Yeah.
Something like that?
Absolutely. The transformer?
Yeah,
Oh, yeah.
it helped that much.
Including when,
Even those of you that are in my class, did it help that much?
I mean, I will say I'm still, like, it made me feel a bit better about it. I'm still like iffy myself. I mean, just because math is like never been my strong suit, but.
But what the thing I want you to understand is your math is P over IE in turns ratio. That's all your math is. And so when you look at the book and what the book explains to you, they give you this ES over EP divided by IP over IS. What the fuck are you talking about? Just show them the turns ratio.
Yeah, that kills me. Like,
It kills everybody, especially because you know what? They don't do step one, step two, step two. They don't make it easy. So what I'm trying to get you guys to do and what I try to teach is say, hey, let's just make this sense. You guys did it right here. 240 into 120, right? That's a 2-to-1 ratio. That's nameplate. That's how it's built. So when you get a nameplate value, that's your ratio. You don't get to change that ratio on basic transformers, okay? I can change my applied voltage though. So if I change my applied voltage, it doesn't change the ratio. That's the hard part. Once you get that part, then you can take your load, you've got power, you've got your voltage, you'll solve your current, right? It's just Ohm's law, P over IE. Every load has 3 components. And we say 4. Sometimes IC is a dick and they put the resistance of the coil in there. Then you gotta find it yourself, but.
I apologize if this is a basic question, but like for Y systems though, like what would you do for turns ratio?
It's based off a coil. I'm gonna show you how to do it the proper way. It's a good question. We'll go over that. I'll make sure that we go over that.
We just want it to be Friday.
You just want it to be Friday?
And it'd be over.
You want it to be Thursday at 10 o'clock with a good score walking out the door, right? Yeah, I get it.
10:30.
That's what we're gonna say, 9:30, that's right. Mark wants you to be done by 7:30, but trust me, I get it. We're instructors. But hey, we're gonna talk about that at the very end. We're gonna talk about how to take a test.
Okay.
Those of you that struggle, how many people panic when it's test time or quiz time? Get nervous. Stop that shit. It's no more than a homework lesson. Stop it. I tell people all the time. It's not open heart surgery. Don't get upset about it. Don't stress about it. Stop studying the day of the exam.
I think I stressed because there's a dollar value.
I get that. There's consequence, right? Welcome to life. That's how it goes, right? I mean, there's consequences. I get it. And that can be stressful. But stress doesn't help you. And that's where I tell people all the time, like in my class, I don't care about homework scores. I don't care about the quiz scores. If you don't take the time to do the homework and put in the legwork, every single one of you should get at least 10 points for showing up here. It's the same thing with people online. Well, people online get 8 because these people actually travel. Okay, sorry, online people, I'm just kidding. But you know what? Because you're showing me effort. There's 600. We have maybe 70 here. Less than 10% decided to come to review. We'll see how many pass. But you're showing effort, so effort should mean something, right? And so that's why it's important to you, and that's why you're here, it's dollar value. Plus, not only that, don't you want the education? It's what you do for a living. This is gonna make or break you. This decides what you're gonna do in life, so I think it's important. Okay, I'm off the soapbox, back to where we were gonna go. Let's go real quick, we'll kind of go down some things. Let me ask this, let's just start it this way, because I can pick questions out of the review, and then I'll let you guys have a session time to pick some questions out of the review, and if we run a little bit over, I don't mind going a little bit over, okay? So if we stay here till 12:30, that's fine, we'll figure it out. Single phase transformers. How does everybody feel about single phase transformers? Do I need to go over them real quick? Do you guys feel comfortable with them? Huh?
I'd go over it.
You wanna go over it? Okay. Single phase transformers, especially what we're gonna do is, let me see. I did do some basic ones. Okay, I'm gonna stick with the basics. We'll start basically and then we'll kind of show some things that progress a little bit. On a single phase transformer, I'm gonna draw them pretty basic. I draw them like this, H1, H2. Even though the book does it backwards, it's okay. Okay? And once again, everything starts in the transformer with turns ratio. Okay? 120, 24 volt. How do you solve for turns ratio? The way you solve for turns ratio is take the smallest number and divide it into both.
Yep.
Best way to do it. 24 into 24 is what? 1. 24 into 120? 5. It's a 5-to-1 voltage ratio. This is the voltage ratio. Here's what we know about transformers. If power in equals power out, that means if the power stays the same, if the load stays the same, if I adjust voltage, then I must inversely adjust current. So what is my current ratio? I don't need to do any math. It's what? 1 to 5, right? Okay. You're like, how does that work, Cal? How can that be? If I'm 5-to-1 and I'm 1 to 5, well, it's simple. Let's say that my load here is 1200 watts. Power in equals what? Power out. Ohm's law on transformer windings. P over IE. Okay? I already know my voltage. 120. 24 volts. Okay? I know I'm at 1200 watts. What's my current? This one's easy. We can do it. On. P divided by E.
That's not it.
What is it?
See, I want to go over.
Isn't it 10 amps? All right. This means it's what? I don't even have to do a calculation. This is 1, that means this would be what? Yeah, 5 times greater. 50. If I don't trust it, I can check it. 50 times 24 probably equals what? 1200 watts, because power in equals
Power up.
power out. If I have 1200 watts on the primary, I have 1200 watts on the secondary. But notice what happened. When I lowered the voltage, the current went up. When I raised the voltage, the current went down. They're inversely proportional, always. We shipped it clear across the office building at 120 volts because it only drew 10 amps. I was able to push to number 12. Once we got to the load, we had to push number 8 because it was 50 amps. That's the beauty of being able to transform power and voltage. Think of it on a larger scale though. So, ratios don't change. What happens down here?
22.4 volts.
Oh, if it's still 5 to 1 is what you're saying?
Yeah,
Okay.
my input voltage was 112, not 120. What happens?
22.4.
Great. The load didn't change. The load still drew what? 1200 watts. That's what the load draws. Will my current value change then?
Yeah.
Yeah, it will. Why? Because I changed my voltage. If the load stays the same, if I change voltage, then I'm changing current. So what happens now? I lower the voltage. I'm supposed to put 120 in. I put 112. This number will probably go up, will it not? What did it go up?
10.71.
Because instead of 120 volts, I put in 112. I lowered the voltage, so it raised the current. What happens to the secondary current then? It also is going to go up. If primary current goes up, so does secondary current. 10.71 times 5?
53.55.
Everybody see what happened right there? Load doesn't change. Loads have ratings at their applied voltage, and that's what they are. That's why you always find the resistive value of that load, add its rating, and you will find out where it needs to be. If you change voltage or current on that load, you're going to change voltage and current. It's why we have things that happen on motors on 3-phase overloads, because motors will operate at 2 horsepower, at 3-phase, single phase, and single pole breaker phase. Remember, 3-phase voltage is higher by 1.732. So if I have a motor that draws 208 3-phase, it actually has 360 volts to it. If I lose a leg, it goes down to 208. When I lower that voltage, what happens to the current going to that motor? It goes up enough to where it smokes it. And you'll learn that in 3rd year. That's why we have to put overloads on any 3-phase equipment, because it will still run on 2 hots. But we went from 360 volts when we had 3 phases down to 208. When I lower the voltage, I raise the current. And then that piece of equipment smokes. Same thing happens with transformer ratings. Now I'm pushing more current through my transformer. Is it rated? Well, we would have to check. If we sized our transformer at 1.2 at the nameplate rating, yeah, this was only rated for 50 amps. When we change the voltage, we're running more than 50 amps through our transformer right now. What could we do? Smoke it. Does that make sense to you guys? Because transformers are rated for what their nameplate says. If that nameplate says 1200 watts at 120 volts, that's what it's rated for. That's why we have to rate transformers with the efficiency. Because maybe I have a 1200 watt load, but with the efficiency, it really needs to draw this. That's why they all have efficiency ratings. Okay, everybody pretty good with this? Pretty simple on the turns ratio, right? Okay. 3-phase transformers are the exact same thing. Except you don't use line values, you use coil values. 3-phase transformers are nothing but 3 of these connected together. You're like a basketball player.
That old Nike commercial,
Yeah, right?
start making a feed with it.
Speaking of, I guess I didn't watch much of them. I'm not a big basketball fan, but it's kind of funny how it changed last night. I was flipping back between things. Nuggets were down 104 to 103. 3 minutes left, and all of a sudden it's like 124, 114 Nuggets. I'm like, fuck. I take it that thing's still good. Okay. Delta? What? Go back over this again. We're gonna do a very common delta Y that you guys see all the time, okay? And I'm not so much concerned with load and things, but what I am concerned with is I wanna make sure that you guys understand where the relationships are, so that when you do get a problem, you can fill it out. Every delta Y problem that you're going to see on your test, on your quiz, on your things, if you draw out what I tell you to do right here every single time, you cannot get it wrong. This doesn't lie. There's no mystery here. There's no trick here.
Trick.
There's no trick. This transformer is gonna be a 3-phase transformer. It's gonna have a 480 volt primary. It's primary, okay? It's going to have, my secondary is gonna be 12208. Okay? And we can come up with whatever we want as far as a load, or if we just wanna size the transformer. So why don't we do this? First, we'll start with just a basic size transformer and show you the relationships. Then we'll size one of these based off a load. Does that work for everybody? And so that you can see the values? Okay, fantastic. So we're gonna start this transformer off to be 112.5 kVA transformer. Don't necessarily have a load on it, but these are all of our givens. Okay? We have values. Okay, we also have circuit types. What type of circuit is this? It's parallel circuit. Don't think of it as primary. What type of circuit is this?
Series.
Maybe that's what I'll do.
Well, the picture parts of them make them look the opposite, don't they? Come on, that looks like a series circuit,
That one does?
triangle.
Yeah, you know why? But you're looking at it the wrong way. Cause you see a loop.
Yeah.
I don't. Which way can that voltage travel? Everybody looks at the circuit itself and not looks at input and output. Even if this was an output to a secondary, how many coils contribute to that phase? 2, that makes it parallel. Go over there, input or output, right? Right here. This one right here, how many coils contribute to that? Or how many do I put into there? It has one path to go. That makes it a what? A series circuit. It's how you perceive it, right? How you look at it. Every single transformer has 2 parts, a line and a coil. I always draw the line up top. E line, I coil. Oops, I line. I don't know what I was thinking. E coil, I coil. Now there's 3 parts here, right? I told you transformers were what? Other than turns ratio, they're pi. We're missing P. We have our line P, it sits up top. This will also have an E line and an I line. It also will have, we'll put it, yeah. An E coil. And an I coil. Okay? What's nice about secondaries is they give you both. Especially on a Y. We know our series and parallel rules. We can figure a lot of this out. Let's start with the primary. Primary is what type of circuit? Series or parallel? Parallel, that means voltage does what?
Stays the same.
It stays the same. So I know that my voltage applied is 480 volts. And that means that my coil voltage is 480 volts. Okay? Here's what I want to make sure that you understand. These transformers here are single phase transformers that look just like that. These are 3 separate windings. This winding is 480 volts connected to or next to that winding, which is 120 volts. The relationship is between the coils. You cannot find turns ratio in a 3-phase transformer from line values. You have to do it from coil values. You know why? Because I have another coil right here. And I have another coil right here, and every single transformer that you've ever opened, that's 3-phase, that sits on the floor, you can look at it and there's 3 coils in it. You see in the one in the lab, there's 3 coils to it. There are 3 individual single-phase coils that we connect together to make 3-phase. So the relationship, the turns ratio in a 3-phase transformer is between the coil voltage and the coil voltage, not line values. The only one that keeps it that way is the delta delta. Why? Because the delta delta is exactly the same. Voltage stays the same in a delta delta. So the line voltage is exactly the same as the coil voltage. Which is why when they gave that stupid example, it pissed me off because like it only works, using primaries and secondary line values if it's a delta. This voltage changes. So the relationship is here. We know that this is 120. So because this is 120, I have a voltage ratio of what? 4 to 1, correct?
Yeah.
What would my current ratio be then?
1 to 4.
1 to 4. That's my current ratio in the coils, not in the line. Does that make sense to everybody? Yes, no, maybe? Okay. Everybody good online so far? Next thing. Ding. I know how to solve for 3-phase current, right? Okay, you know how to solve for 3-phase current, right? So, we're just gonna do maximum values that this transformer can handle. We know what my load is, quote unquote, or what my transformer is rated for, okay, is what? 112.5 kVA, there's my P. We're gonna do the primary first, primary, what's P? 112.5 kVA, okay? Is this a 3-phase calculation? When I'm dealing with lines? That's okay, I'll answer it. Yes, it is. I can hear the guys online, I can't hear you guys. Look at it. Yes, 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 sir. Fuckers. Let's go. Okay, we know this, right? Do we know our voltage for the primary?
Yeah.
Yes, we know it's 480 times 1.732, which equals what, guys? 831, right? Yeah, do you guys remember how to do that? Okay, cool. So take 112,500 and divide it by 831. Just Ohm's law. That's all it is. 112,500,
135.3.
135.3
Or 135.
We'll do the point. Everybody understand how we got there? We had watts. We had voltage. What did we solve for? Line current.
What was the last one after the 831?
Well, it's Ohm's law. We're looking for current, right? Just solve for current. Yes.
Why doesn't that line current change though? Why is that?
Does change here. Does change here. Doesn't change here. This is parallel circuit. This one. Okay. So we know what my line current is, right? What is it?
135.
135.3.
Yep, 135.3. Yep. We'll do 135 for now. It's easier, got more room that way. Okay? What stays the same in a parallel circuit? Voltage, okay? That means current must change. Because we went from three phase, which is 831, really, down to single phase, which is 480. Okay? How much less is coil current than line current?
4 times.
No. This is within this thing itself. It's not the ratio over here. It's less than 1.732, right? So when I'm within my circuit, when I'm within my delta or my Y, right? And the delta is parallel, so voltage stays the same. That means my line values will be greater than my coil values by 1.732. Or think of it reverse, coil will be smaller than line by dividing it by 1.732. So if I take 132 and divide it by 1.732, what do I get?
So 135.
Huh?
So 135.
Well, 135 divided by 1.732.
77.
Okay? Does that make sense? Okay, I want to show you something. I'm not looking at the Y at all, and I'm not looking at the ratios at all. We're just solving the delta. Okay? So are you with me so far? Right? So we know that in a delta, voltage stays the same because it's a parallel circuit. We agree with that, correct? Okay? We know that we have our KVA up here. That's the load up here. Okay? Voltage stays the same. Line current is greater than coil current. I always draw my line up high because it's always greater. Line is always greater. So in the Y, my line voltage will be greater than my coil voltage. Line is always greater. So whatever doesn't stay the same. Here, it's current and KVA. Both of them are always smaller than coil. Does that make sense? Oh, good night. Thank you. Okay? So this is our, this goes back to single phase, right? Because it's a coil. Does that make sense? It's part of a three-phase system, but this is a coil. Can I solve for power right here?
Yes.
I can, right? Don't I have E? Don't I have I? It's not three-phase E, it's only the coil, it's single phase. This is one phase. So this is single phase value. Does that make sense? So I'm gonna take E times I. What do I get?
3,739. No, 37,392.
37.39 kVA. In any circuit, whether it's delta or it's Y, coil power is additive. That load plus this load plus that load, guess what it equals? That load. You know how else to find how much each kVA is worth in your transformer? Take your total kVA and divide it by what? By 3. So here's the thought process on the delta. Delta is a parallel circuit. Voltage stays the same. Line values are greater than coil values. Current 1.732. Power divided by 3. I take this plus that one, gives me that number right there. Okay? I can do the same thing on the other side. In fact, I'm not gonna do the same thing on the other side. You're gonna do the same thing on the other side. So look at it. Power in equals what?
Power out.
Shit, do I already know my KVA right here? Yeah. I'm gonna know my KVA down here. I can solve that shit per se. How about this? KVA. Right? My KVA is 37.39. Can I solve for my coil current? Look what I got. I've got 120 volts single phase. I got 37.9 KVA in power. Can I solve for current? Yeah. How do I solve for current? P divided by E. It's gonna give me current. What would be my current?
311.5.
311.58. Cool. What stays the same in a series circuit?
Current,
What's this value up here?
311.58.
What's my voltage? Here's my wattage. Thanks for coming. If you do this and break it down each way and you solve that, doesn't matter. You can solve anything. Now, here's the great point. Where's the ratio? Here. Right? Coil to coil. What's my voltage ratio? 4-to-1. Look at my current ratio.
1-to-4.
Yeah, 1-to-4. Everything stays the same as if it were single phase transformer.
I'm still so confused as to why, like, the 831 isn't really acknowledged, like, on the line value.
It is.
It is like in the amperage calculation, but like, because it's a parallel circuit, it's like, we're just seeing 480 on both
But
sides.
this is 360. That's three phase 208 is 360. Do you know why? We don't have 3-prong meters. In the field, you're gonna put your meter on there. What do you read on a 3-phase circuit? When you look at a 3-phase band and you check voltage, what do you see? 208. Because we don't have a third prong, we don't have a third hand. We can go boom, boom, and boom. We'd see 208 times 1.732. We'd see 360. Does that make sense?
Yeah.
The reason we don't say 831 up here, because we know it's 480 volt, 3-phase. So we're just gonna take that times 1.732. That's this voltage right here. That times 1.732 is this voltage. This is 480 volt, 3-phase. This is 380 volt or 280 volt or 480 volt single phase. Right? And I think that's a big confusion for everybody. That's a big concept that people forget because it's easier to remember the 1.732 to add the voltage every time you do a 3-phase calculation. But it goes back down to the point of this. If I have one hot and neutral, okay, and we can go off of this one here, it's gonna be 120 volts. If I have two hots, it's 208. But if I have three hots, I have to take the 208 times 1.732, or otherwise known as 360. Well, we don't have a meter, so nobody recognizes 360. They're like, 360, where'd you get that from? What type of panel does it have to come out of? Well, you would have to divide it by 1.732 to figure out that you could come out of a 122.08 volt panel. Does that make sense? So we just use this as 208 3-phase, 208 single phase, 120 volt. Same thing here. 480 volt 3-phase. 2 hots would be 480 volt single phase. 3 hots would be that. When I have 3 hots, my voltage is gonna go up.
So that's why each coil is worth 120.
Yes.
Wow. Yeah.
So 120 to 120, you're thinking 240, but I've got influence from here. But in series circuit, remember, voltage doesn't stay the same, current does. Hot to hot, 208. Hot to hot to hot, It's actually 360 volts if you add a third leg on the meter, but you don't. So we call it 208 three-phase. They have 208 single-phase. That's the difference. So anytime you have 308, just change your voltage. 208 three-phase is not 208. It's 360. We just don't label it that way anymore. Too much print. You just know that anytime you put three-phase voltage, you have to have 1.732 added to it. Okay? So does everybody understand how this relationship works? Right? Okay? So we're gonna do the same thing, but in a little bit different scenario. Two ways, Ben. One, I could just do my single phase voltage times my single phase current is gonna give me single phase power. Or I could take my total KVA and divide it by 3. Once you understand the rules of this is Ohm's law. Three-phase transformers are 3 single-phase transformers. Within your coil is Ohm's law. P over IE. That's it. First year shit. Make it any harder than that. When you get three-phase, work it backwards. Three-phase is P over IE. What do you do to voltage then? Multiply by 1.7.
I will say sometimes it's, and I said this last time, but sometimes it's how they ask it or how they draw it, where it's confusing.
That's right. You should just draw it yourself and look at what they're looking for. It's easier that way. So let's say I have this. We'll keep this kind of the same.
You mind doing a couple more examples
That's what I was gonna do.
It should be like,
out of the
Well,
book?
if we
I mean,
could-
out of the outline,
Big one.
20 and 21?
Really with this single phase.
Yep, that's what it's all about. We'll do some examples now. 20 and 21. Okay. So these aren't transformers, these are loads. Okay, but it's pretty easy to kind of figure out where we're gonna be with this. It's the same principle, okay? So 20 says refer to figure 401. The ammeter 3 indicates 45.8 amps. The duct heater is delivering how many Ks of power? Okay, so what do we know? What's my power supply to my load?
277, 480.
Is it three-phase?
Okay.
Fantastic. So question number 20, the first thing I want to find out is what's my power? So my power, my voltage, and my current. Okay, what's the question asked again? Put those 3 up there. It's delivering power. It wants to know this question right here. Okay, so let's go down and find out what do we have? What do we know? We said that it's 3-phase voltage, right? What's the 3-phase voltage?
277, 480.
Okay, cool. So I'm shipping 480 volt to my load, right? It's a 3-phase load. That's no agreed. Okay, so it's gonna be 480 volt 3-phase, correct? Coming from a Y, which is 480 volts, 3-phase, okay? Do I have a current? I do, right? Yes, no, maybe. 45.8, right? Isn't that my line current? Let me ask you a question. I line goes with what? E line, right? Yes, no, maybe. Especially on my load. What's my load? A delta. Line current isn't the same as coil current, my delta. But this question asks where amp probe 3 is. Where is amp probe 3? It's on the line. They're asking for line values. Hey guys, you have line voltage, which is what? It's a 3-phase circuit. It's 480 times what? 1.732. I have line current. Solve for line power. It's this formula right here. P over I line E line times that right there. So I'm gonna take 480 volts multiplied by 1.732, which is 831. Times what?
45.8.
45.8. What do you guys get? Yep, 38.07. Would you get E? Right, close enough. It depends if you take it all the way out to the square root.
Yeah. Shortened this.
Don't forget, it's three-phase voltage. You have to multiply it by 1.732 because it's line voltage. Line current, line voltage. Even though it's only one leg, it's line. Okay, now here's the kicker. Refer to the same drawing. Is the winding or coil current flowing through the power supply in winding A equal to the floor or the current flowing in heating element A? Are they the same system? Are they both Ys?
No.
Okay, they're different systems. Agreed?
Yeah.
So would they have different values?
Yes.
Okay, is it safe to say we can keep this, right? What do we know that our system is right now as we speak? When we look at our power supply, because it's line. Okay? 45. Okay. Just gonna try to remember this stuff off the top of my head, so if I forget it, you guys can help me. Here's my Y. Now this is what's different. This is a secondary that's physically attached, okay? To a load. These wires, I always hate doing this because I always screw it up. But we're just gonna pretend one set of wires, okay? That's it. We have E coil, we have I coil, we have E line, we have E line, we have E coil, we have I coil. Agreed? Everybody with me so far?
Yep.
I line and I line. We determined that this system was what? 277, 480 volt three phase, correct?
Yes.
We figured that this voltage was 480 volts. Would anything change from here to there?
No.
No, it's the same. Okay, we determined the current, or we didn't determine, they told us the current was 45 point what? 8, right? Okay, 45.8. What type of system is this? Y. What stays the same in a Y? What would this be?
45.8.
45.8, fantastic. What type of system is this? Delta. What stays the same in a delta? Voltage, great. If these stay the same, this must change. Agreed? If this stays the same, 45.8, 45.8, what must change? This, agreed? We know this value here is less than because line is always greater. Line's greater, I always draw it on top. This equals 277. Over here, this stays the same, this must change. How much does it change by? The square root of 3, right? So I'm just going to take the 45.8 and divide it by 1.732.
26.4.
If you can draw it and solve it, now go back to your question. What does your question say? Refer to the drawing. If the winding coil current flowing through the power supply in winding A equal to the current flowing in heating element A, they're asking you about coil and coil. Is this coil current the same that's flowing in this coil current? No. They're two different systems. If it was a delta delta, would it be the same? Yes. If it was a Y Y, would it be the same? Yes. But it's not.
That's a test.
So for the, for 20 though, I missed the answer on that. Was that, I line times, you know,
No, no.
45.8 times 480 times, square root of 3?
You gotta take your voltage times the square root of 3. All with their voltage only. did you write down what I told you the other day about the 3 different voltages at 3-phase?
I believe I did.
Okay, anytime you see something 3-phase, use those values instead. So if you wrote down 480 times 1.732 is 831. If you wrote down, then you could just do basic Ohm's law with those values. Like I have it memorized, and most people, when you start doing it, you'll get that way. So anytime I see 208 3-phase, I no longer think of 208. I think of 360. Does that make sense? Then you can just do a basic Ohm's law calc, right? E divided into KVA, boom, right? So if you can get yourself, train yourself to memorize those numbers, 480 volt equals 831 at 3-phase.
So that, it was E for 20? Yeah, it's E.
Yes. Yes. Sorry, to get to your question, yes. Shit, 3 pages. Damn. Look at all you. I like it. 75 people online. Man, but the free food here has been fantastic, hasn't it, guys?
Yeah.
It's all right, it's not over, like, we're gonna have to eat.
And the open bar, it's been great. Mimosas all day long, Bloody Berries, fantastic here. Yeah, make a little bit more sense? Okay, what else, for examples on the transformers, do you wanna hit? Take your time.
23 would be nice.
23 would be nice. Okay, we can keep going down here. Total opposition of current flow in the electric current is called resistance
It's fun.
in a direct current. Oh, 22, that was 22. I'm sorry, you said 23, right?
Yes, sir.
Showing my age. A 45 kV transformer is fed from a 3-pole breaker and a 277 480 volt panel board. I love IEC's thing. We gotta give a description. They're not just gonna tell you, they're gonna make you figure it out yourself. The transformer then supplies power to a 120 208 volt 3-phase 4-wire panel board. The transformer has 2.2% impedance on the nameplate. The available line to line voltage short circuit fault current on the secondary is how many amps? Okay, so here you're just solving current, right? Does the question make sense? Or you just lost in what the question's asking? Or how to do it? I mean, I get you're just wanting to know how to do it, but what's the question asking you to solve? Amps, right?
Amps on that.
Did it give you KVA?
Yeah.
Did it give you voltage? How do you solve for amps? That's all it is, but you have to do something special to the voltage. Multiply it by the impedance, right? That question is the short circuit fault current question. They sound really complicated because look at all the information. Good night. We had a 480 volt transformer, blah, 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 blah. Okay? The secondary is what voltage? 120/208. Okay? So basically they're saying, look, I got a 120/208 volt system. I have a fault current. I wanna know I. Now the I is going to be short circuit. Once again, transformers, nothing changes. Except here, we have to multiply this by the percent of Z. And we just take straight voltage. We don't have to do 831. We don't have to do 1.732. We just take the 208 because it's between phase to phase. Does that make sense? It's not between A phase hit B phase hit C phase. It's A and C phase had a fault. Does that make sense? Makes it single phase. So people are like, oh, let's say 3-phase panel though. Shouldn't that be 1.732? Not when you're solving short circuit. All you're doing is this. That's it. We're looking for I. Except we have to take voltage and do this. So if you can do that formula, it's ISC equals VA, or you could do KVA, I'll put KVA, divided by, in parentheses, E times the percent of impedance. Okay, so let's fill in the blanks. What do we know? We know it's a 3-pole breaker, blah, 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 it's 120. We know it's 208. Right? And we know the impedance is 0.2 or 2.2%, which we're going to change that number, right? That 2.2% isn't really 2.2%. Okay, and we're gonna divide it by what? Or divide it into what?
45,000.
45 kVA, that's correct. 45,000 would be great. Okay? So this number right here is really 208 times 0.022. Remember, we gotta move this to a decimal. So 0.022. What's 208 times 0.022?
4.57.
4.57. Does everybody understand where we are right here? Everybody understand how we got here? Anybody not understand? Okay? So now we're gonna take the God, that's gonna be close, that's a lot. 4.57 divided into about 4.5. 4.5 and 45,000, we're gonna figure this fault current out pretty quick.
1,833.
Yep. 9,833 or so.
0.9, yeah.
That's close enough to get the number. There you go. That's my fault current. Hey, guys. Write this down right here to solve short circuit fault current. This is current. This is power. That's this right here. It's Ohm's law. It's a transformer calc. What did I tell you about transformer calcs? There's only 2 calculations. Right? P over IE and turns ratio.
For the answer,
Mhm.
this one I had to use in the 732,
It actually using the what?
1.732.
Line to line?
I got 9846, but it's 9834. I guess it's just because you didn't use the whole thing.
On the answer key, it says that?
Yeah.
Well, look where they used it on though.
Probably get 5.
That's because they use 2.2%, use 2%. No, you did.
No, that's right.
It's because they used the 1.732 as well.
Might have messed that up. Voltage fault current. Yep, you're right. It's 3-phase. Well, let me just completely mind fuck you all now.
Oh, my goodness.
So we're using 360.
Yeah. I was used to the 208 volt when they said single phase fault current.
Okay.
I just thought single phase fault current.
Right, in pencil.
So it says 3-pole breaker right in front of it. All right, let me try this again.
Well, this is somebody caught it.
Single phase fault current. My bad. Yeah, like I'm gonna trust him now.
But there's a formula for it too.
I know, I saw it. I was like, I just read the single phase fault current is what I read. It said single phase fault current. That's why I wasn't paying attention to the 3-phase system. Which, you know, my fault. It's all about fucking details, right? 3-phase. Okay, my 3-phase ISC. Damn it, IEC tricked me. That's what you guys would say. Okay, Those are the two formulas, my bad, I apologize. Okay? Single phase fault current. No 1.732. Make sure you look at the system, not what faulted. Three phase fault current, 1.732, that's gonna change our answer, isn't it? It should change our answer, because when we multiply by 1.732, we increase that voltage, and that percentage is gonna change. Now we're gonna have a higher voltage into the same KVA. And so it changes it. It'll be less. Said I'm leaving. It's actually much cooler out in the hallway than it is here. Well, there's nothing to do with the doors being wide open. Come on in. It's better. Does that make more sense? So write it down in your notes. Single phase fault current. And at the end of the day, you guys should be able to look at that formula and just write it out on paper and put the values below it. I know you can do it. Just trust the formulas. I'll tell you a quick story, real quick. Second year, not to brag or anything, but I was a top student in second year. I was fucking lost. I could not get magnetic induction through my head. Couldn't get it. But the reason I got that and I did so well in it is I trusted the formulas. And it wasn't until third year when we did a quick transformer review, that one day I was sitting in class and I went, bink, and I went, oh shit, it's that simple. Literally, it clicked just like that. Changes for some people probably already have it. They're sitting here because they want to make sure. Some people it's already set in stone and you're good to go. And some people it hasn't set yet. Just because it hasn't set yet doesn't mean you won't get it. You will, I promise. I'm telling you, I didn't get any of this induction shit until third year. And it was one stupid class, 20 minutes on the board, and all of a sudden I'm like, oh my God, motors clicked, transformers clicked, everything just clicked. Then it was like, it cannot be that easy. I kept telling myself, it's really not that easy. And I'm like, yeah, it is. And it wasn't in the way that he presented it, it was just Ohm's law. God, this wheel does everything that you guys need to do. It does 90%. If you don't have a sticker, get one at the front door. Put it on your notes, put it on your calculator, put it wherever. At the end of the day, it's Ohm's law. What's the question asking you and what did it give you? And draw out Ohm's law. Hey, it asked me this, it gave me that. What do I have to do? And if it's three phase, make sure you read the question properly. And two, do that. Great, now I got a 98. Yes. Yeah, you do use it for E-line.
I will say, it seems like, I don't know if it's the calculator, both answers that I'm getting are just like kind of nominal from what the actual answer is.
Well, that's probably, did you extend the 1.732 out all the way? Did you do the true screw,
I did the,
true screw?
just like the
Can't say square.
3 square root, yeah.
3 screw root.
Yeah, did you do the true square root of 3? Or did you put in 1.732?
I did the true square root of 3.
They might have used 1.732, they might have used 1.73. It's, once again, it's all who wrote this and put it together.
Yeah.
So whatever that person used, sometimes they round up, you ever notice? Sometimes they round up, sometimes they don't. You're gonna get close, none of them are that close to where it will matter. I think you can use the square root of 3 if you want, I just use basic numbers to get it close.
So how are you gonna trick
Huh?
us? So how are you gonna trick us if you wrote the test?
I'm not gonna, so here's the thing, I don't get to write the questions, I get to pick them from a test bank. I would love to write questions because they would be nothing like these. Well, somewhat, some of them, but some of them I wouldn't. We used to write our questions, but we have to use from a universal test bank to make it fair across the nation. See, and that's kind of what happens when you guys talk about plans and prints and things, you guys really need to speak up and write constructive stuff on your surveys. Because there's people in this country, small chapters, that really feel that blueprint reading is the most important thing for their crew. Because what they want to do is train field electricians. And so blueprints is massively important. I don't have time to teach them in the field. You guys work with anybody that says I don't get paid enough to teach somebody? I hate that. Really? How'd they get to where they are? They learned, they were just stuck out there and they learned it on their own.
That's why I hate when they switch me over from one journeyman to another. Parts of it I like, but then sometimes I'm like, you know, some of it's just so important.
I
And
think-
you can actually learn from somebody who's willing to teach you versus somebody who just wants you to do the shit and tail work and not learn.
That's life.
Yeah,
And you know what? Unfortunately though, some of the things that make a difference for me, that made a personal difference for me. This is for me. It's not IAC's philosophy. This is not anything like that. For me, I worked for a small shop. So I was lucky because I got to stay on the job from start to finish.
mhm,
So I got to do it all. I got to do underground, I got to do trim, I got to do rough, I got to pipe ceilings, I got to do all that. And then I'd bounce from guy to guy to guy, whoever needed help. So when the job was over and this guy had a big project, I'd go work with him. And there were guys that I did not like.
mhm.
There were guys that didn't have journeyman license that could run work, but they couldn't pass the test because they never went to school and they didn't want to, and school wasn't mandatory. And here I was with a higher license, they're running the job and I'm looking for them. Right? They like to do all the panels. I'm gonna set the panel on, we get the conduits out, you guys do all the other shit. But you know what? You do it with a smile, you learn the best with the best, and you appreciate the ones that you work with. Big shops are a little bit different. I've met people in second year that haven't left the fab shop. Or they're nothing but on trim crews. And for me, working for a big shop has its pluses and minuses. I'm not gonna talk about a big shop. I've never worked for one. And it may work well for some people. Chance for advancement, things like that. But I like the small shop. I like the experience of getting out there and being able to do a little bit of everything. That was for me. I'm not saying all you guys go work for a small shop. That is not what I'm saying. Big shops have great advantages, probably more so than smaller shops. They pay a little bit more, a little bit more sometimes, because they can. Different types of work, cool work. But yeah, I've met people that have done nothing but do trim. Fab shop to put in plugs and switches.
Mhm.
And it's unfortunate. And hopefully they get that experience. They can get onto a one line crew where they do nothing but build gear. And then they can get on a rough crew and they can get on a, hopefully and those are things that you need to speak up as an electrician and say, look, I've been on this trim crew for 6 months. I'd like to try something different. Can't hurt to ask if you do it the proper way.
Mhm.
Some people aren't built to teach. How many of you guys are gonna be instructors when you graduate? Or how many people go like, fuck school, I'm out. Trust me, it's more of that than there is people that want to teach. You have to want to teach to be a good teacher. But like I tell every single foreman, you're only as good as your crew.
Mhm.
If you don't help your crew, they're not gonna help you.
Yeah,
I'd give my crew goals. You meet this goal, we're leaving at noon. I'm gonna screw the shop, we're gonna put down 8 hours and we're gonna go have lunch on me. My crew busted ass, they got the shit done, boom. I took them out to lunch and beers on a Friday afternoon. Thanks for coming, thanks for busting your ass, I appreciate you. And my jobs did good though. Guys wanted to work on my job. It makes a difference. You're only as good as your crew. All right, back off the soapbox. Let me see if I can get the next question right. What else do you guys want to know? Oh,
Can we look at 28?
28, yeah, we can look at 28. Transformer connections. I love transformer connections. This is why I like them. The one thing you have to remember about transformer connections, because you're never gonna memorize every single transformer connection. But what you can memorize is series and parallel. When it comes to transformer connections, it's all about output voltage, right? And input voltage, right? So that's what we need to remember. When we're doing transformer connections, the one thing I want you to focus on is in a series or a parallel circuit and what are the rules. When it comes to voltage in a series circuit, E total equals what? E1 plus E2, right?
Mhm.
It's adding. In a parallel circuit, right? E total equals E1, which equals E2, which equals, and so on and so on, correct? Yes, no, maybe? Okay, cool. If I have a secondary that has 2 voltages, do you remember those rules? In series, each winding is additive. In parallel, each winding is what it is. So if I have a secondary windings. Try to get a little bit darker so everybody can see it up there. Primary winding. Secondary winding. Okay? This one's worth 12 volts. This one's worth 12 volts. Okay? Remembering my winding values. When it comes to parallel or series, I know that if I make my connections in series, it's E winding 1 plus winding 2, correct? So if I want 24 volts, I want to make this additive, which means I need to connect them in what? Series. One path in, follow it. I have to do what? I have to come here, go like this, and out. I put them in series. That's 24 volts. Parallel, E1 equals E2 equals E3. Well, if E1 equals E2, well, whether it be primary or secondary, it doesn't matter. I'm gonna hook them up in parallel. My output voltage is 12. Right? Does that make sense? So I can take that value on any type of question I look at. If I want high voltage, I'm gonna hook it in series. If I'm gonna take the lower voltage, I'm going to hook them in parallel. The best way to identify it is series always takes 2, ties it to 3. Every single time. High voltage always takes 2 and ties it to 3. So look at 28. Is that the connection you wanted? Is that the question you wanted, 28?
Yes.
Okay. So it says, which of the secondary winding connections shown in figure 215.52 is, oh my gosh. Is used to connect the proper supply, is correct to supply the proper voltage to the 240 volt load. Slow down, Cal. Okay, what is each winding worth on the secondary? It tells you. They're worth what? 120/240. That means each winding's worth what? 120. If I want E1 plus E2 to equal 240, I have to connect them in what? Series. So that means I have to have 2 and 3 tied together. And the outputs would come out of what? 1 and 4, right? Or 1 and 1 as they have it over there. So yes, drawing number 1 or answer B would be correct.
So if you look at drawing number 4, are you only getting 120 out of that diagram?
No, that's the combination, the good old, I'll tell you what happened in that drawing right there is I shorted that whole transformer out. You know how I shorted it out?
You overloaded it?
No, I took X4 and tied it to X1
Yeah.
and bypassed all the windings.
Mhm.
Now, if I were to take that X1 wire and take it to the load, that would be a 120/240 volt connection.
If you had your 1, your 2, and your 4 all connected to your load,
So if I did, yes, so if I did this in that example,
would you call that a series parallel connection?
basically it's 120/240 volt connection. So what we do here, right, this is worth 120 and this is worth 120. Did they do 1, 2, 3, 4?
They did 4, 3, 2, 1.
4, 3, 2, 1, yeah, same difference. 4, 3, 2, 1. So this would have given me, if I go to the load, right? This and this give me my what?
240,
My 240. If I take this wire down too, then it gives me my
120.
240, 120. So from here to here, 120, from here to here, 120, but across the two is 240. So if I needed a load that was a 240, 120 volt connection, I would draw it like that. But what they ended up doing is they took this thing right here, right? I don't know exactly what they did, but they went like this.
Yeah.
Over to here. Once I did this, I bypassed that winding. Now I just shorted it out.
Gotcha.
Got nothing.
Thank you, sir.
You're welcome. What else? 38? Okay. So that's just asking you what? Okay, is it a transformer question?
Yeah.
Okay, what are the three things in a transformer? Hey, I can point to it. What's the three things in a transformer? Power, voltage, and current, right? Are those the three things in a transformer? Every transformer has this. KVA. It has amps. And it has voltage. This voltage is dependent on whether it's single phase or three phase, so make sure you read the question. Okay, what'd my question say? You said that was 38, right?
Yeah.
It's a 480 volt to 240 volt three phase transformer rated for 112.5 kVA. So first thing I know, two things.
Mhm.
One, there's two voltages, and the other thing is I know my power. Power in equals,
Power
so I already have power. What's my power? 112.5 kVA. I already have that part, right? Yes, no, maybe?
Yes.
Cool. Then it said, without overloading the maximum available secondary line current. What is my secondary line current? Or excuse me, my secondary voltage? Cause they're asking for secondary. So if I know the KVA, power in equals power out, I need to know secondary voltage, correct? What's my secondary voltage? 240 what? Yeah, make sure you pay attention to that, cause I'll steer you wrong.
Okay.
That's 4.
Yes. And what's it asking for?
Amps.
It's asking for current, line current. It's just asking for this, I. How do we solve for I? We take 112,500, we divide it by 240 times 1.732, which is 415, and we get current.
112.5.
Thanks for helping me out online there, people.
269.8.
$269, which is probably B. I got 271, yeah. Wonder what it is times that.
Just do 112,000. Divided by 240.
Well, it's 240 what though? Yep. I got 270.6, so they're using the actual square root of 3. I came up with the dead nut number when I used the square root of 3 on my 240 volt. I got 270.632. That is correct. I think that's the result. But that's close enough. What else?
You got a buck transformer real quick?
Okay. Do you want to size one? What do you want to do? Because the buck ones are like 46, 47, 48.
I want to buck one. Yeah, 48 would be great.
48 would be great. Okay. So are we bucking or are we boosting? See you later. Okay, do you know the formula for a buck? Find it. Because the buck, I know it's ICV first.
ICB
Minus
minus
OVR
OVR
divided by ICV.
multiplied by KVA.
Yeah, I did that though because we didn't have a boost, so it's ICV first. So question number 48, we're gonna look at that formula, right? ICV minus OVR divided by ICV times the KVA of the load. Okay, so we can fill all of this in. You're welcome. Okay, what's the input circuit voltage?
240.
240, fantastic. Okay, minus, what's the output voltage required? 208. Okay, that means we'll end up, once we solve that part, we're gonna go ahead and divide it by, what's the input circuit voltage? 240, correct? Right? Then once that's closed out, we're gonna multiply it by the KVA of the load. Do we know the KVA of the load? Can we solve for the KVA of the load? How do we solve for the KVA of the load? Yep. What's the load rated at? Voltage wise? 208. Okay, what else did it give us to find that information?
Yeah,
48. Okay, they gave us amps.
volts in our amps.
Okay. So can we solve for the KVA?
3.1, 31.2 KVA. Right?
Well, power in is the same as power out, so you take the primary and calculate that, correct?
But the question gives us what?
You're supposed to be boosting from
The load draws what?
Amps and volts.
50 times 240.
Okay, but why are we going 240?
The load is
Because we
240.
need the 208 volts. Oh, it's fuck loose, yeah.
So when I read this question, we're saying this backwards. This is a boost. This is a boost, not a buck.
Because we're trying to supply
Yeah.
240 and we
We
only
read the
have.
question wrong on this one. I should read the questions.
Uh-huh.
Well, I thought we were doing a buck, right? That's what we said we were doing with the buck. But here's my thing. How do you calculate the load? How do you calculate, let's just start here. Let's just leave it at this for now and then we'll do that, okay? This is not question 48. Let's just solve this though, okay, since we're here. How do you solve the KVA at the very end? Don't you take the required voltage by the required amperage that it draws? So how would we solve this right here? So what we're doing right here is we want 208 volts, right? And what's the amperage? 150. So to solve the KVA, we're going to take the 150 times the voltage that's required here, right? Which is 208. That would give us our KVA. Does that make sense? That's what we would normally do.
31.2.
Okay, 1.2,
31.2.
31.2. Okay, 31.2.
Times 2.
Okay,
Wait, where'd you get the 150? Sorry.
says it in the question. Says it draws 150 amps. Okay. So because we interpreted the question wrong, and I should have read it first. That's not what the question is asking. The question is asking us. So forget about the question. Let's look at the scenario. Our scenario is different. We have 240 volts. We want 208. We're bucking. Okay. So in order to determine how we buck, in order to determine the KVA, we take at what the load is rated at times the voltage that it needs. Does that make sense? Every single time.
Well, I said buckload, didn't I?
You said buck, but you asked to do question 48.
Ah,
So we wrote buck assuming that that was a buck question. That's why it's fucked up. So
got you.
we're just gonna solve this formula first. This is not a big deal. I'm not too worried about this. Okay, we'll figure it out. Okay? This is your buck. Okay? This is your buck. Question 48 is a boost question.
So I wrote it down wrong, that's why I'm confused, sorry. I wrote it down right, I mean.
Either way. My God, people.
Oh, yeah.
We're making this difficult. This is a fun thing. This is not question 48.
Okay, just forget about 48.
Yeah.
Forget about 48 for a moment. It's like the movie Arthur. Why don't you forget about the moose for a moment? Okay? This is just a question we made up. We are bucking.
Oh,
Pretty good? Okay. When we buck,
look,
this is the formula we use. If we were given the information used from the question, as far as amperage and certain voltages, this is what we're gonna go off of. Our load's 150 amps. It requires 208, we're supplying it with 240, so we're bucking. I have to calculate my KVA at what the load draws. The load is everything, not the transformer, the load. So we came up with 31.2. Okay? Let's do the math. 32 divided by 240, agreed?
0.1333,
What is it?
0.1333.
Sorry, one more time. 0.133, okay, times 240.
32.
Wait, is boost divide or times?
You guys have got 6 ways to Sunday right now. It's fucking shit. We're reading every question out loud from now on. You're right, it's divide. 240 into 0.133.
Real quick, we just did that one.
Seriously. I'm gonna punt.
So 0.133 times
Thank you.
31,200.
31,200.
Yeah.
That's going to give me my KVA. Fuck.
4,000,
4,000 even?
4,160, sorry.
Or in other words, that would be 4.16, so we need a 5 KVA transformer. Okay. We're gonna do question 48 now. And I'm gonna read it out loud and make sure that I have it right.
I think it's about the same.
It's close. It's doing the same work, right? It's a 32 volt that's doing the work. We're bucking or we're boosting it. It's still doing the same work. It's close. Okay, I'm gonna read 48. The circuit you have available to supply a 240 volt load. So we're gonna start at the load. To supply a load that's rated at 240 volts at how many amps?
150.
150 amps. So my load, the circuit you have to supply a 240 volt load at 150 amps is 208. So my input voltage is going to be 208. I need to get to 240. I'm boosting. That's what question 48 is. It's a boost. I want to go from 208 to this. So the formula. Start it again. Okay? OVR minus ICV divided by OVR times the KVA of the load. So I need to solve a couple of things. First of all, my output voltage required is what? 240. my input voltage I have is 208, we're still gonna get basically the same ratio. We're then going to divide that number, multiply by 240, right? And then we're gonna multiply that times this number. 36,000, thank you. Or 36 KVA, right? Cause that's what we're gonna keep it, they're keeping it at KVA. Times 36 KVA. Okay? 240 minus 208 is 32. We're gonna divide that by 240, we're gonna get 0.1, right? Times the KVA rating, times 36 equals what?
48,000. Or sorry, 4,800.
4.8 KVA?
Yeah.
So we would need a 5 KVA transformer.
We did 1.333 times 36.
Yep,
I got 47.988.
yeah, close enough to 4.8 KVA. So what size transformer would be big enough to work for that? A 5.
Yep.
Do you guys understand what we're doing right here? Basically, what we're doing is we're taking the amount of voltage that we're bucking or we're boosting, and we're finding the percentage that we're bucking or boosting it of. When we take the difference between these two right here, it's 32 volts. It's what we're boosting. We're gonna divide it by what our thing requires. That means we're taking a percentage. That 32 volts is what percentage of this? That's what happens when we take this number and divide it in here. This is 13.3% of that voltage, because that's the part doing the work. So that means if we're only boosting 13% of the load, then I only need to size 13% of the load. And you're asking, why does that work? Watch. Ready? Watch. Don't be confused, it's all right.
I'm just confused by the answer. 47.9 is anywhere remotely close to 4.8. Right.
Say what?
Like, cause if you do the 1.333 times 36,000, like if you change it to just watts. Still, even when you bring it back, it's 47.9 kVA. So how is that anywhere close to 4.8 kVA? I'm a little confused on that.
No, you're only off by less than 100 watts.
Well, would that be like 4,800?
It is, but it's KVA, stop changing it to watts. It's not, you don't size a transformer out of watts. You don't buy a 75,000 watt transformer.
But even if I did it the other way, it came out as 47.
I know, the book just rounded it up. We just rounded it up.
I'm confused.
You're saying 47 point?
Yeah.
47,000.
Yeah,
Where are you getting 47,000?
that's what I'm saying.
It's because he's changing this.
No, even when I don't, even if you do 1.333 times.
You said it, you just said it, 1 point, it's not 1 point, it's 0.1.
Alright, cool. Thank you.
Okay, so back to here, right? Here was the deal. Our transformer, right, was 32 that we're bucking or boosting, right? This little coil does 32 volts. This little coil does the rest. When we're boosting, like in this example, here's what we're doing. This part is already, it's okay. This part's already got 208 volts. It's flowing through. It's like, yep, we're already here. Remember, we're pushing current. We don't have enough force to get the job done. We need to add a little bit more. The only part of a buck boost transformer, because that load is what? It's 36 kVA. The amount that we have to boost or buck is the only part of the transformer doing the work. Out of 240 volts, we need to gain 32 more volts. So we're gonna take that 32 volts and find out what percentage it is of that KVA load. Because the rest of the KVA load is already coming from the 208 volts right here. Does that make sense? So because we need to boost that voltage, how much work do we need out of this to do that? So we take this number and we divide it into that number. Or vice versa, the 240 volt into that number. what percentage of the 240 that I need is that, and that'll be that percentage of the total KVA I need. So instead of buying a 37.5 KVA transformer, if you change the whole thing and make it isolated, I can get away with adding a 5 KVA transformer and boosting the voltage a little bit. That's the purpose of it. Okay. Just follow this formula.
Okay, Cal, thank you.
Yep, you're welcome. Goodbye. Yep. Remember Rock County now. He's in the last segment. Okay, this right here is just a percentage of what we have. It's 13%. That's how you do it. It's what we're bucking or boosting, amount of voltage that we're bucking or boosting at our load into our total KVA. This KVA would change if I had a different load, that percentage would change. This percentage would stay the same, but it would be a difference in the transformer because this changes. When we buck or boost, I'm still at 0.133. It doesn't matter, 240 to 208, right? Or I mean, excuse me, 208 to 240, that percentage stays the same. This transformer has to buck or boost 1.133 of that voltage. And so that's what it does. So if I am bucking or boosting 1.33 of the voltage, then I have to come up with 0.133 of the KVA. So it allows us to size smaller transformer to get the same result. So basically we got the faucet turned on 3/4 of the way. We just need something to open the faucet all the way. And that's what we're sizing. So if you can remember the formulas, that's the best way to do it. That's what I would do. And then the other thing is I'm telling you all of you, ask your instructor. If you have a question, come up and say, hey, am I on the right track? They may not give you the right answer. Your instructor may say, I don't know, can't help you. But it can't hurt to ask when you test. Last but not least, for those of you that struggle a little bit with taking the test, here's what I can tell you to do, okay? 2 things. First of all, prep for a test. How do I prep for a test? What should you do to prep for a test? Take time to study, make dedicated time. Don't do this whole thing at once. Do 15 questions, spread it out over 3 days. 15 questions, do in order. These questions are set up as the homework is in the book. So it's pretty easy to tell what chapter they came from, okay? Take your notes. You get a question wrong, copy it down, copy the answer down. How did they do it? Draw it out, okay? Eat before you come here. I don't care if you're late, eat before you come here. Get something to drink, eat before you come here. Don't study test day. You know what you know come Monday, Tuesday, Wednesday, Thursday, or Friday. You know what you know. Smoke your brain before you get here. That's a great idea. Unless you have the day off, I wouldn't do it. Okay? Organize your notes. This is circuits. This is buck boost transformers. This is 3-phase transformers. This is 3-phase loads. Get those stupid little stick it tabs and put them on your notes. And so that when you go to a buck boost transformer, you can go right there, flip to that thing and look at it. Okay? And then the other thing is how you take the test. I'm going to tell you, nobody does it. I'm telling you to do it. You should read your test first. Read your test. If you can answer that question off the top of your head, just like that, answer it. If you can't, skip it. And this test is easy. You can put it into 3 categories. When you take your test and you know the answer, great. If you don't know it, what is it? It's a circuit question. Resistive, inductive, parallel, blah, 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 blah. That goes in one column. It's a single phase transformer question. It's a 3-phase transformer question, or it's a buck boost. And write the question number down under each of that column. Then when you go back to take your test, answer all the questions that deal with buck boost transformers first. Answer all the questions that deal with 3-phase transformers second. However you want to do it. What it allows you to do, and this is basis off the code. I do this on code tests, and I'm going to recommend this on the code test. Because you're going to be bouncing around if you don't. These don't go in order. When you get your test, you're going to get a 3-phase question, then you're going to get ohms is measured in what? No, X of L stands for what? Buck boost transformer size. This 3-phase load, here's a single phase connection. Back to a 3-phase load. You're going to be all over the board. So if you don't have the tabs and can't do that, isolate your test into sections. And it's simple. Answer the ones you know right away. The ones you think you know, answer them next. The ones where you don't have any fucking clue, save them to the end. I will tell you, I've had people take a journeyman's test where 60% of the questions, they're like, I have no fucking clue. The first time around, they answered under 40 questions. But you know what screws you up even more? Is getting into your test and you get 3 hard questions in the first 5, and then you set yourself up for what? What happens to you?
And-
Do you panic? Do you get frustrated?
Mhm.
And then you start missing simple shit.
Mhm.
You start missing the simple things. What is it that I have to do? Man, why did I make that so hard? I was just so frustrated, man. It's late. I'm tired. Yeah, because you didn't read your test first. You never got to question 48 before you were smoked. And question 48 was power n equals. And you screwed it up. You knew it, but you were so tired, you didn't get it right. So that would be my advice on taking your exams. Eat, be right, bring your stuff here, take breaks. God, I watch people take tests here, nobody takes a break. You guys sit here for 3 hours and don't even get up and move. I'm like, what are you doing? It's just a second year midterm. Get up and take a break. Ask a question if you have to. Study the review. That's all you can do. But organize your notes. That's probably one of the most important things to do. Make sure you understand what your notes say. All right. I think we're good. 12:30. Unless you guys online have anything that's massively important. Were you guys online? Real quick, hold on. If you have any questions, like on a Tuesday or Thursday night, you don't take a test that night, that means you're not taking your exam that night.
Thank you.
You're welcome. There's my phone number. Whoops, you should have gone to everybody. That's my phone number, you can text me.
This,
Yeah,
no, how we got this answer.
because it's 3 phase.
Once we got this, I just get up in this.
So, so it's just this Ohm's law. So this number here, hold on a second, let me see this. This number here is this in parentheses. So do your voltage first and get your 831. Now solve for your current. 112,500 divided by 831.